Hello ladies and gentlemen, I'd like to welcome you to my speech today as part of the web seminar of the RILEM conference Micro Durability in 2021 now, and it is not in Den Haag but here in Brunswick, in Braunschweig in Germany, in my office, where I am working at the Institute of Building Materials. I am a PhD student, my name is Stefan Ullmann, and I am working under the guidance of Professor Loke. Behind this quite complicated title that I picked almost 1.5 years ago, we have three main things we can focus on. First is chloride ingress in repair mortar. Second would be coupled loading conditions, and that means in this case chloride ingress while a certain external load is applied. And the third one would be an effect, a possible effect of the Young's modulus of the repair mortar that we are testing. The chloride migration coefficient is classically tested in the laboratory using the experimental setup from Antibuild 492. The question is only, is there a direct comparison possible between a value that is tested in the laboratory and the concrete that is really included in the building? We have microcracks appearing, also chemical attack. So in our eyes there is a certain gap between the lab testing and what is tested on site. Not only we but also other researchers before identified this gap. What we try to do in the work in my PhD thesis is to build a bridge between this gap or over this gap and to do the chloride migration test under loading. This is the content for today's speech. I will further on show my experimental setup, followed by the results, and finally we make a conclusion and give an outlook. Let's have a look at the materials we used. We used 3 different mortars for our experiments. Those were 2 PCC mortars and 1 CC mortar. Please don't get confused by the naming. We used PCC for polymer cement mortar and not concrete, as well as CC for cement mortar and not cement concrete. Sorry for that. The recipes. We have some main differences we can identify between the recipes, and that is in the maximum size of the aggregates. The CC mortar has a maximum size of 3.50 mm. The PCC mortars are finer in their aggregates. They have 2 mm and 0.8 mm. All 3 materials we used ordinary Portland cement, and what is worth noting is that the PCC mortars contain PP fibers. A look at the harden properties, next to some differences in the compressive strengths, we also have a very broad range of the Young's modulus. And that was our goal, to use materials with a broad range of the Young's modulus in order to point out certain effects that are caused by the Young's modulus on the later on tested dependency on external loading. The tests were conducted for 24 or 48 hours, dependent on the material, and after 28 days of curing. To perform the rapid chloride migration test under load, we designed a certain loading frame which allowed us to apply an external load along the peripheral surface of the RCM disc. After the specimen were loaded, we set up the whole experiment that looked like this. To the left and to the right we had the containers for the cathodic solution. And after the test it was important that we took care about the directions of splitting. So as we marked here, we had 4 different directions. We made quarters out of the specimen, and that was due to the appearance of the cracks, as we see on the left side. The main cracks, which were some macro and also micro cracks, more important the micro cracks at the lower load levels, they appeared vertically, and that is why the directions 1 and 2 were the ones that we analyzed afterwards. Here we see an example for a split sample in the directions of 1 and 2, and we see the lighter color is the front of ingress of the chloride. The brown surface is not in contact with chloride. Now, for the analysis of the split sample, we need to take a closer look. For all the samples that were loaded at 0, 40 and 60% of the ultimate load, we had a quite smooth front of ingress that only varied by the mean depth. When we take a look at this picture, we see the front of ingress of a specimen that was loaded with 80% of the ultimate load, and we see that at the edge regions 2 main cracks appeared, where the front of ingress was much higher than in the mid section of the specimen. If we depict the way of analysis that is proposed by the anti-build, we can see that it is quite a coincidence if we can measure this main depth of ingress or not. Maybe the point is just next to it. And that is why we chose to differentiate when we do the analysis. Later on in this paper you will find some graphs that lead back to uncorrected values or to corrected values, and that means that we included or excluded these main cracked areas in the edge regions for all the 80% load specimen. This is an example for the uncorrected values. We chose the 2 main depth of ingress and accompanied these with 7 mean depth of ingress. And the second part would be to choose 9 mean depth of ingress and to exclude the main cracks. Now, here we have the results. The ones we depicted here are absolute results, so referring to the non-steady state chloride migration coefficient directly. It is depicted on the y-axis, and on the x-axis we have the load that we applied as a percentage of the ultimate load. So 0, 40, 60 and 80%, as well as 100 in one case. All these points represent the mean of 2 to 4 single results, and we depicted the uncorrected values as I showed you before, including the micro cracks on the left, and the corrected values that refer to the mean depth of ingress only on the right side. What we see is that the non-steady state chloride migration coefficient of the cement mortar changes significantly due to the applied load, and it changes significantly from the point of up to 50% on. And that is also for the corrected values, as we see. Not as heavy, but it can also be detected. But what we also see is that the PCC mortars are almost not affected by the external load. Only if we apply up to 100%, almost 100%, then we can see a slight increase. But if you want, we can also try to interpret a decrease of the chloride migration coefficient, a slight one. And what I just showed you becomes even more obvious if we depict the results relatively. So referring to the non-steady state chloride migration coefficient that was determined at 0% loading. Again, we have the uncorrected values, including the macro cracks on the left, and we have the corrected values on the right. We see again that the CC mortar is much more affected by the external load than the PCC mortars. And what I did not point out so far, and what actually was the intention of the investigation we made, the Young's modulus has an effect on the impact of the external load. And that is what we see when we compare the 2 PCC mortars again. The PCC1 mortar, that is indicated by the triangles, lies slightly above the PCC2 mortar that has a lower Young's modulus than the PCC1 mortar. To conclude, referring to our investigations, load-induced cracks do affect the non-steady state chloride migration coefficient of a CC mortar. And we noticed that the value increases beyond a load level of around 50% only. That was also noticed by other researchers, and other researchers did the same work on concrete samples. When we compare these results with our results, we can see that the increase that we noticed is less obvious than the ones that were noticed on concrete samples. Generally, we saw that the effect of an increasing non-steady state chloride migration coefficient dilutes with an increasing Young's modulus. And from our results, we could also say that external load even improved the chloride migration resistance of the soft PCC samples. Let me give a short outlook on the work we presented here. We had the impression that the size and the amount of aggregates also seems to have an influence on the formation of the microcracks, the crack width, and also the number of the cracks. And due to that, we have to say that for the evaluation of an increase or decrease of the migration coefficient, it is very important to carefully decide where and how the analysis has to be made, as larger cracks strongly affect the value but do not represent the influence of the microcracks throughout the whole cross-section. Thank you all for listening to my speech today, and I would also like to thank not only you but also to the German Research Foundation that financed my work and is financing my work still throughout my PhD. And I would also like to thank the researchers at the Department of Sustainable Built Environment at the Queen's University in Belfast. Thank you again, and enjoy the rest of the Micro Durability 2021. Bye bye from Germany.